All right, so we're going to now look at the way that this inductive method, the foundation of science, is used in what's called the scientific method. Now, you may have been taught a scientific method that looks something like this. Simple list of you ask a question, do some background research, construct a hypothesis, test your hypothesis by doing an experiment, then analyze your data and draw a conclusion, and finally report your results. This is a typical way of outlining the scientific method that's presented to grade schoolers and even high schoolers across the country. One problem is it's woefully inadequate. This is not how scientists really do their work. The way that science is really done is a bit more complicated and looks something like this. You have all of these different processes feeding into each other. There's feedback back and forth. You can jump in at any point. You don't have to start at any particular place. It's not a list. It's a cycle. And as you go through the cycle of observations, observations may want to make you define the problem differently. And once you start asking questions, you may want to go back and do some more observations because you realize you have some problems in defining your problem or your question. You make some investigations about what is known, you carry out some studies and do some experiments to find what is unknown. You articulate your expectations ahead of time, maybe in the form of a hypothesis. But the exact order that you're doing this in can be a little complicated. Things go back and forth, and everything is moving towards a goal of a theory. And we talked about before that's one of the general goals that all science is moving towards, is developing better and better theories. Those are these general principles that you conclude through the inductive process. These theories, these general principles, are feeding into all of the work that's done by scientists. This method here of reasoning is being used all the way along the way. You're using evidence and data and observations to back up your theory through all of these different steps. And what's really important over here, as you see, is that you're communicating your findings to society and to the scientific community. And that's key, that's crucial, something that a lot of people forget about, the communication aspect. Scientists don't do their work out in solitude in a basement somewhere just on their own. Occasionally you can find out a few things that way, but the best science is done in community. And even brilliant minds like Einstein were constantly feeding off of the work of other scientists and communicating with other scientists, and that is vitally important. So, now, let me erase that. So we can go over, just to make sure everything is clear, we're going to go over some definitions, basic definitions that are used by scientists, words that you've all heard before, but they have maybe a slightly different meaning when used in a scientific context. So when we talk about things in science being scientifically proven, this means a little bit different, something a little bit different than in mathematics, something being mathematically proven. Mathematically proven means essentially you used all your logic right. You didn't make any mistakes in your logic, and you came up with a proof that nobody can really argue with, assuming you're using the same axioms of mathematics. In science, when we say something is proven, we mean that it's supported by many lines of observational evidence. So evidence is the key here. Proofs have to do with this convincing evidence and not just logical arguments. Facts in science are observations or measurements, and that's really all they are. So it is incorrect, and even scientists will do this sometimes, but it is incorrect to refer to theories or principles in science, overarching ideas, to refer to them as facts. The theory of gravity is not a fact. It is a theory that describes why certain facts happen. By themselves, facts may not be particularly interesting. It's when you collect a lot of facts together, then you can develop a theory, and that's what we're really after. And then scientific theories, as I've been talking about, these general conclusions about the way the world works, they are always well tested. When we're using this term correctly, we're referring to ideas that are well tested. They are not opinions, guesses, or untested ideas. At that stage, we refer to them as hypotheses. But once they have been tested, we can start to call them theories. And hypotheses are also more commonly used for very specific experiments with specific outcomes. You have a hypothesis of what might happen. But a theory is developed as observational evidence starts to all point in one direction, and you develop an idea that is supported by that data and by that experiment, by those observations and those facts. Okay, a few other words. We talk about models in science. And in science, models are ways of representing the natural world, but they do not necessarily provide an accurate picture of everything that you're talking about. So, for example, the atomic model, let's say the Bohr model of the atom. In the Bohr model of the atom, you have a nucleus here with so there's some protons and some neutrons in there, and then outside of that you have some electrons orbiting. And you may have lots of protons and neutrons packed in there. Okay, that's a very useful model of the atom. It tells us a lot of things about the atom, but if you were to peer at an atom with a microscope, you would not see something that looks like that. It doesn't look like the solar system on a small scale. It's very different when you start to examine an atom at small scales in detail. It does not look like this at all. That doesn't mean that the model is wrong. It just means the model is limited in its usefulness as to what it can do. It's very useful for telling us about energy levels of electrons and certain things about the general size of atoms, but it does not tell us what an atom really looks like. Scientific hypothesis, I've already referred to those in reference to the scientific method, but a good hypothesis, I want you to understand, should include three things. A good hypothesis is not just this guess, it should explain the current data that you have. It should predict the outcome of the future experiments and observations, and lastly, a good hypothesis should be falsifiable. That means that here's a statement that you're making that you can imagine creating an experiment that could prove it false. You're hoping that it doesn't prove it false. You're hoping that the data and experiment backs up your idea. But you have that option of being proven wrong. If there's no option of being proven wrong, it's what we call unfalsifiable. And if it's unfalsifiable, is generally a pretty poor hypothesis. Some scientists say it's not even scientific at that level. There's a little bit of debate depending on which scientist you talk to, but it is definitely not a very good hypothesis if it doesn't meet that criteria of being falsifiable. So keep that in mind if you think about developing a hypothesis for an experiment that you're going to run. You want to not only just predict what's going to happen in your experiment, but you want to be able to explain why and then have something that's falsifiable. Leaving you with a couple of quotes. Henri Poincaré, who was a French physicist and philosopher, said, "Just as houses are made of stones, so science is made of facts, but a pile of stones is not a house, and a collection of facts is not necessarily science."